Okay, so this is expression for celerity of a elastic wave. Okay, consider this to be the rigid pipe, and in rigid pipe a close fitting piston is there. So this is the first position of the piston. This dotted line shows the second position of the piston. Okay, this is wave front which is traveling with velocity c. Okay, now this distance between the first position and second position of the piston is x, and x is equals to v into dt, where v is velocity of travel of the piston, dt is a small time for which the piston is traveling. Then here from the piston at a distance of L, okay, this wavefront or disturbance is moving. This L is equals to c into dt, c celerity and dt small time. Okay, let us see the details. Consider an elastic fluid at rest in rigid pipe. So this pipe is said to be rigid, that means it will not change its shape, size, etc., etc., but the fluid is elastic one, so its elastic properties are need to be considered. Elastic properties simply means surface density. Okay, so the cross sectional area is A. So next, V velocity of the piston, P pressure of the fluid in the pipe before movement of the piston. Okay, rho density of the fluid before movement of the piston, V uniform velocity of the piston towards the right hand side for small time dt, c velocity of the disturbance pressure wave. Okay, or velocity of sound wave in the medium. Okay, so during small time interval dt, the piston will move towards through a distance x, that is equals to v into dt. So the earlier piston was here, now it has come here. Okay, and the pressure wave will move forward through a distance L is equals to c into dt. Okay, so the pressure wave will move forward with a distance L, c into dt, c velocity, dt time. Okay, due to movement of the piston through distance x, the fluid in the length of tube L minus x, uh, uh, total distance is L divided by L minus x into this, in this region, the fluid will be compressed. Okay, the fluid in the length of the tube L minus x will be compressed. Okay, density of fluid in this length L minus x, earlier it was rho, now it has become rho plus d rho. Okay, small increase, incremental increase in rho. So pressure has also changed, p plus dp, so in this small part, L minus x part. Okay, next, by continuity equation, so mass before compression is equals to mass after compression. No problem. So mass before compression, mass density into volume, rho into A into L. Okay, we know it. But mass after compression, density into volume again. So density now changes, rho plus d rho into area as A, and volume L minus x. Okay, or length is L minus x now, earlier it was L. So equating both these two, rho AL is equals to P plus, rho plus d rho plus A into L minus x, this as it is. So what remains? A cancelled on both the sides. Rho into L is equals to rho into L minus rho into x minus d rho into L minus d into rho into x. Okay, so what remains? We are interested in finding out L, d rho into L. So this is d rho into L. This we are interested in finding out. So this is equals to x into rho plus x into d rho. Okay, x into rho. This rho L get cancelled. X into rho plus x into d rho. This is okay. Next, L, but L is equals to c into dt and x is equals to v into dt. We know these equations earlier. So L into dp. Okay, L instead of L you put c into dt into d rho is equals to v into dt into rho. So x is equals to v into dt. Okay, plus v into dt into d rho. Okay, so what is there? C into d rho is equals to V into rho plus V into d rho. Okay, now next thing, but as V and d rho are very small, hence their product is neglected. Okay, this quantity is neglected, so what remains? C into d rho is equals to V into rho. So why there this is neglected? Huh? Consider V very small and d rho very small. Okay, so their product will be much smaller. And if this V and d rho can be neglected, then product is can be neglected safely without any harm. Okay, so C is equals to rho into V upon d rho. Name this as equation 1. Okay, now due to moment of piston with velocity v for time dt, the fluid particle uh, have acquired a velocity v. Okay, and the pressure on the fluid has increased from p to p plus dp. Okay, applying momentum equation, force is equals to rate of change of momentum. So force is equals to p plus dp into a minus p into a is equals to mass times mass upon time into change in velocity. Momentum, change in velocity by time, into mass. So next, a into d rho a l upon dt into v minus 0, change in velocity. So v is a final velocity, initial velocity 0. So this all turns out to be c is equals to dp upon rho into v. Okay, I think the video is getting quite longer. Okay. So multiplying equation 1 and 2, what we get? C square is equals to rho into V upon dp into, sorry, d rho into d rho divided by rho into V. Okay, so finally C square is equals to dp upon d rho, or C is equals to dp upon d rho, or C is equals to square root of change in pressure upon change in density.